Hello, and welcome to this presentation on automated Arctic coast erosion mapping with ENVI 5.0 and ArcMap 10. We're presenting live from ExcelSviz offices in sunny Boulder, Colorado. Thanks for attending. The rising temperatures accompanying current climate change trends have an exaggerated effect at high latitudes because of the increased duration and distribution of summer ice-free conditions along the Arctic Ocean coastline. This has amplified important coastal processes and resulted in outsized examples of rapid coastal erosion and change throughout the region. Areas in the region dominantly composed of ice-cemented peats and silt-rich permafrost have proven to be especially susceptible to rapid erosion. Recent research has measured erosion rates at sites along the Alaskan Arctic Ocean coast of 15 to 20 meters per year or more. Certain records have it as 24 meters or more along the Beaufort Sea. Here we can see 1 month's worth of erosion from a fixed camera in July 2008 near Drew Point, Alaska. The land and marine resources and ecosystems of this region are all heavily impacted by coastal morphology and dynamics, as are the people and nations involved and their competing claims. For most of the Arctic coastline, there are few or no historical maps and little to no detailed geographic information about the coastal morphology. Gaining a sufficient understanding of the Arctic coast for safeguarding territorial, resource, scientific, and environmental purposes requires not only a current map of the coastal morphology, but mapping the changes and trends over time. In addition to the challenges this region presents due to its rapid changes and lack of historical data, the area under consideration is enormous. The Arctic Ocean has roughly 45,000 kilometers of coastline. Finally, it is an extremely remote and inhospitable region. These factors make manual, ground-based, or field studies difficult and expensive at best and impossible at worst. The combination of ENVI remote sensing analysis tools and Esri GIS technology is the most effective and efficient way to map coastal change at regional to continental scales. To meet the challenges of mapping Arctic coastline change and trends, we need to be able to cover a regional to continental scale in an objective and repeatable fashion that is cost-effective with regard to both time and money. To address the data portion of the problem, we can use Landsat archive data to cover the region starting as early as 1972. With revisit times as frequent as every 2 weeks, we can get reasonable assurance of cloud-free data at least once per summer over the region. The Landsat archive has also been geometrically corrected to level 1T specifications, ensuring the best possible spatial accuracy of features given the resolution of the data. We have 60-meter pixels for the earlier MSS imagery, and 30-meter pixels for TM and ETM imagery up to the current time. Moreover, the Landsat archive data is also freely available. Hand digitizing the Arctic at the level of detail required to capture coastal morphology and change would be entirely impractical from both cost and time perspectives. ENVI feature extraction will not only clearly delineate the coast as best as possible from the imagery data, it does so in a deterministic, parameter-based, reproducible fashion that can be set to run in a programmatic batch mode. This removes the need for an analyst to supervise the process and permits the analysis to run as fast as our hardware and storage systems will allow. Automated feature extraction results have been shown to be comparable to results from human image analysts for tasks like coastline delineation. Better yet, the automated results are repeatable. With the generous assumptions shown here for manual delineation and conservative assumptions for the automated processing rates, we can see ENVI and ArcMap could be run together on a small cluster to produce comprehensive pan-Arctic Ocean coastline change maps for the last 40 years in perhaps a month or less. The biggest concern would be the data storage needs, which may approach 40 terabytes. For this study and demonstration, we've focused on a much smaller sample area. To completely automate the process, that is, to have the image analyst completely removed from the loop, there must be some level of a priori information to ensure the accuracy of the feature extraction classification. Fortunately, most of the world has at least some level of GIS data for coastlines. The data are not always at a resolution fine enough for coastal morphology, and they may not be very current. However, even coarse GIS data can be used to sort image segments in areas about which we have high certainty, and then use those regions to characterize the remaining image segments about which we're less certain. Esri's tools for the buffering of and selection from multiple GIS layers are the ideal choice for this analysis. Here we can see our study area in the Drew Point region on the north coast of Alaska, as well as our GIS layer for the coastline. The polyline is a reasonable approximation at the continental level, but in detail we can see it is too coarse to capture coastal dynamics at scales of less than several hundred meters. And it's only a single snapshot in time. We need to map changes and trends over time. However, we can use it as a coarse sieve to help separate those image segments for the land and sea, and use those for our certain pieces of the analysis. Our first step in this method is to use ENVI feature extraction to find all the edges and regions within our image. Here we can see what the automatic image segmentation results look like in ENVI for the entire Landsat MSS scene for 1974. Even with widespread thin clouds and sea ice, the coastline is very clearly delineated by ENVI feature extraction. With ENVI feature extraction, we can count on consistent results using only two input parameters, segmentation and merge. For MSS data, we use a segmentation value of 60 and a merge value of 70. For TM and ETM data, we use a segmentation value of 70 and a merge value of 90. In experiments here, we have found that the coastline is a strong enough feature that there is a wide tolerance in the usable settings. So it's not important to even exactly use the segments and merge values mentioned. Next, after we've done the segmentation for the whole scene, we use ArcMap to combine the extracted features with our known coastline layer. Here we see the roughly 40,000 feature-extracted polygons from our 1974 scene overlaid on our coastline data. For the next step, we use Esri's powerful selection tools to get only those segments that are not part of the buffered coastline. We're using a 3-kilometer buffer here. Fourth, we again use the selection tools to separate those segments into land and ocean classes and pass them back to ENVI. So only segments that are landward of our coarse coastline by at least 3 kilometers will be used as land-based polygons, and those seaward of the 3-kilometer buffered coastline polyline will be used as training segments about which we are certain they are ocean. Those segments passed back into ENVI for our 5th step will let us rerun feature extraction with exactly the same segmentation and merge parameters that we used in the first step. However, this time we continue through the classification option in feature extraction and use our Esri selection tool results as the training data. The new classification result looks like this, with no human intervention or input. Although our initial polyline was coarse and our training data were not perfect, after all, there were some lakes in our land class and some ice in our ocean class. There were also sensor artifacts and clouds. But we can use the law of large numbers and rely on most of our tens of thousands of training polygons to be usable examples for classification. Better yet, we can run this GIS-refined feature extraction classification for each image in each year in a batch fashion. At this point, the feature extraction from and GIS-based classification of the imagery have produced a map with two classes, land and sea, for each year for which we have data. For our sixth and final processing step, we map the location and magnitude of coastal change in terms of lateral erosion or deposition. We use this by mapping it with ENVI's thematic change detection tools. The tool compares the two-class land-sea data from year-to-year pairings. Areas classified as land at time 1, but then classified as ocean at time 2, will be written to a layer recording erosion areas for the time 1 to time 2 interval. Areas classified as ocean at time 1 and classified as land at time 2 will be written to a layer recording deposition for the time 1 to time 2 interval. Areas of no change will not be noted or recorded. This will save processing and data storage space. Also, because we're using feature extraction and the thematic change tool rather than a spectral comparison tool, we're able to use different sensors over time, in this case MSS, TM, and ETM data. This also eliminates calibration processing. This simplifies our workflow, maximizes our chances of having historical data coverage, and saves time in our workflow as well. Now that we have our methods established, we need to automate them for them to be useful at the scales that we're interested in. Because ENVI is written in IDL, every step in ENVI can be scripted as a completely unattended batch job. Furthermore, because ENVI and ArcMap work together seamlessly, the entire job can be encapsulated and run in batch from ArcModeler, calling the correct Esri and ExcelisViz tools in order and on the right data to map the Arctic coastline and how it changes over time. The user could start the process by pointing the model script at the data storage. The script will send each image to the ENVI segmentation only process. Because ENVI and ArcMap are integrated, Esri's tools can automatically ingest those image segments, compare them to a global coastline vector available freely from ArcGIS Online, and buffered to 3 kilometers. Every segment landward of that buffered coastline will be classified as land. Every segment seaward of the buffered coastline will be classified as ocean. ENVI will automatically see these classified segments and use them as training data in our second segmentation and classification run through feature extraction. That'll produce a final two-class land and ocean image. This process will be repeated in ArcModeler for each image, and then the thematic change detection will be run. Here we see an example ARC model where ENVI's thematic change detection is run from within the toolbox in ARC. This model, along with other models and tools from ExcelisViz, automatically install in ARC Toolbox when you install ENVI. The models are editable and can be used as templates in developing your own integrated ArcMap and ENVI tools, such as this workflow. Finally, the erosion and deposition layers for all the time periods analyzed are combined in ArcMap. This will produce a comprehensive map of coastal morphology and change. Here, we have erosion from 1974 to 1978 in the Drew Point, Alaska area, shown in yellow. 1978 to 1999 erosion is shown in orange, and 1999 to 2011 is shown in red for erosion. There are clearly portions of the coast more actively eroding than others. Also of interest, we have deposition shown, that is, new areas of land. For 1974 to 1978 deposition, we're using light blue. From 1978 to 1999 deposition, we have dark blue. And 1999 to 2011 deposition is shown in green. Important features here are that the areas of deposition are concentrated around coastline spits and river deltas. This suggests that the melting and erosion rates of the permafrost at the coast and inland are sufficient in volume to exceed the carrying capacity of the coastal transport dynamics. This results in these concentrated areas of deposition and are clearly visible in later imagery as spits, deltaic deposits, and sediment plumes. Further analytics and models could be run from these layers, or they could be combined with other layers, such as ocean currents, temperature maps, precipitation records, geologic maps, or landform maps. Here, because Esri and ExcelisVis software are integrated, we've created a plot in IDL of net erosion rates in the study area based on an analysis of the layers in ARC and then exported into IDL. Current erosion rates in the study area are at their highest level since 1974. Running further analysis on finer pairs of years would help in better characterizing the trends and variance in the yearly rates and fill in the gaps between 74, 78 to 99, and 99 to 2011. In this preliminary study, we've shown that a completely automated approach to mapping the Arctic Ocean coastline and its changes over time is possible using Esri and ExcelisVis technology. We found a few possibilities for further work and analysis as well. First, we can only map what we can see. Our process will work even if it's a little hazy, but opaque clouds will cause problems. Detecting opaque clouds and excluding those regions from processing would be a useful addition to the model. Other studies have shown that this can be done in automated processing. Second, similar to the clouds, we need to have the coastline visible. That is, our process won't work if the shore is obscured by ice that is contiguous across both land and sea. Similar to opaque clouds, other studies show promising results for automating the detection and exclusion of these problem areas in our workflow. Also, with the maximum efficiency, possible only with ENVI and ArcMap automation, the data storage required to map the whole of the Arctic Ocean for the last 40 years is daunting. It's around 40 terabytes. Taking an intermediate step and processing just a single region, say the Alaskan coastline or the Scandinavian coastline, then mosaicing just the change detection results might be a more efficient way to achieve a complete understanding of Arctic Ocean coastal erosion processes over the last 4 decades. Finally, while we started out with a coarse GIS layer and buffered it to start our training data, it is possible and may improve accuracy if, once we have a first base map of the coastline from the imagery, we could use that as a sharper training set and a sharper coastline polyline, and refine our results progressively as the map becomes more defined through the time stack. These are all realistic challenges that can be solved with Esri and Excelis technology, and the results would be truly illuminating in understanding Arctic Ocean coastal dynamics, and only requires further tuning our ARC model implementation. This concludes our presentation. If you'd like more information, please email us at info@excelisviz.com or visit our website at www.excelisviz.com or visit us on Facebook, Twitter, or YouTube. Thanks again for your time and interest. We will keep the chat open for questions, and we will have the live Q&A question and answer panel open as well. Okay, our first question is feature extraction part of ENVI? It runs from both within ENVI and ARC. It is, however, available as a separate module from ENVI. A basic install that won't have it. It is activated as a licensed feature. a question here. It says, will this work with higher resolution data, such as WorldView 2? It actually does work very well with WorldView 2 data. I've used that for some coastal mapping at more tropical latitudes. The only reason I didn't use a higher spatial resolution here is we needed to go back in time far enough to get erosional trends. And the Landsat archive allows us to go back to 1972, whereas most of the available high-res imagery will only go back to about 2000 or so in the areas that we're trying to cover. See, there's a question that says, will the presentation be available from the website and YouTube? It will. We are recording it, so we will have that posted shortly. Let's see, does feature extraction in ENVI 5 work only with ArcMap 10, or it could be integrated with ArcMap 9X? I have seen it run with the last version of 9X. Actually was running it that way last fall, so that should work for you. There are some nice features in 10 that does make it a little smoother, but it should work. Question, do you have to calibrate images from different sensors before comparing? For strictly morphological studies like this, where we're only grabbing land and ocean, because our change detection is based off of the thematic layer, we fortunately don't have to actually do the radiometric calibration or the atmospheric step. If we were going to do a spectral change-based comparison, then we would need to. Fortunately, with feature extraction and the thematic base, we are able to skip that for this particular study. If you wanted to compare, say, levels of vegetation health, then you would need to do a radiometric calibration, atmospheric modeling, and then actually compare spectra to spectra across time. Because we can do this just at a morphological level, it allows us to use different sensors as well. That's a good question here. It says, I understand this model it's critical to have very good geometric corrected images and mosaics. Otherwise, there could be misclassifications, erosion, deposition. That's very true, and prior to the level 1T data being available, I had tried this with the less corrected data, and you would get misclassifications. Typical shifts in relatively flat coastal areas would be on the order of several pixels, so it would have been off by on the order of 100 meters, which is, of course, coarser than what we're looking at here. However, the Landsat archive has been reprocessed, and what they call level 1T is an orthorectified product available directly from USGS with NASA assistance. And the accuracy there has compared well with studies with USGS and University Colorado Boulder studies as well. So yes, it is important to have your geometric pieces lined up ahead of time. So the question here, will running scripts require IDL? The authoring of scripts requires IDL, but you do not need an IDL license to then run them. They can be compiled, essentially becomes a runtime application. So the question here, would this work with SAR data? Actually, it works very well with SAR data. I have done some Arctic ice mapping with that. The main issue we had here is the SAR data were not available as early as I was hoping for. As you can see from that earlier plot, the erosional rates were moderate in the 70s to 80s, dropping down into the late 80s, 90s, and then drastically picking up starting about 1995 or so up to the present time. With the SAR data, I was only catching the last part of that trend, so in order to extend my historical range, I had to use optical image available earlier. If you do have SAR data, though, it will work very well with feature extraction. The great part about that, too, is you're not at all concerned about clouds, and at high latitudes like the Arctic, you also don't have to constrain yourself only to the narrow couple of ice-free, well-illuminated months in the summer. So another feature extraction question. Is the algorithm used in ENVI fundamentally different to that used by Adrisi? The range and segment size seems greater in ENVI than Adrisi. Perhaps this is actually more about user settings than fundamental differences. The specific algorithm between the two is different. However, what they're doing at a qualitative level is basically the same. Most feature extraction algorithms run some sort of an edge detection filter first. And then really how strong that filter kernel is, what we call segmentation setting. It's often called scale or size setting in other packages. There are different ways to go about that. There are double watershed algorithms. Some gradient filters are popular as well. We have several options available, and you can toggle between them in the workflow and specify them, of course, in an IDL script. Each one is detailed with the citations of original papers available in the documentation, so you can be sure to use the right one for your particular situation. So yes, it does come down to the user settings versus any real differences that the algorithms will do. Well, thanks again for everyone's time. We'll keep the chat open here as well. I do say I've got 2 more questions just popped up. We'll answer them as well. Let's see. Will Maris modus data be too coarse for the model? Will they be useful to pinpoint more critical areas with less storage requirements? Modus would work very well for our largest time span. You could probably go from earliest modus flights to current day and catch maybe the most severe areas of erosion, but you wouldn't be able to do single-year pairings. If you're losing at most 20 to 30 meters of coastline in the most severe areas, the larger pixel size of modus wouldn't allow us to capture just 1 year's of erosion or a trend, in addition to its possibility of not going back as far in time as the Landsat archive. However, it would be useful on larger change detection pieces based on feature extraction. There's been some very nice studies doing basically this model on, say, urban development and sprawl. That would probably be an excellent area for that. And you're correct, it would, with the 500-meter pixels or 1-kilometer pixels, it would take up a lot less space than 40 terabytes, which would be useful. See a question in, if I want to compare images based on spectral changes, how can I calibrate the images? The easiest ways to do that, if you want to do it interactively, if you search for calibrate under your ENVI 5.0 toolbox, a number of calibration tools will show up there. I believe there's about 10 to 15 different sensors. We can also apply gain and offsets if you happen to know those for the sensors. And the atmospheric correction module would allow you to model and apply atmospheric correction for both multispectral and hyperspectral if you have it. So you would be able to get them onto a common basis that way. And then to actually compare the spectra, I would recommend using the image-to-image change detection workflow. The nice part there is you don't have to run through the classification step first. So that would allow you to work on, say, water quality differences or, say, vegetative health differences, possibly even sedimentation or pollution mapping as well over time. Thanks again for time. We'll keep chat open and monitor for questions. Please visit us at www.excelisviz.com. Or if you think of questions afterwards that you'd like to ask, email us at info@excelisviz.com. Thanks again. Have a great day.